Hello, I'm Felipe Zanon and I'm speaking from Brazil. Today, I'm going to present the paper written by me, Dr. Ozzy Leal, and Dr. Alberto De Conti. So, one of the main challenges that we have for transient events is to model them well. For this, there are models that are less or more rigorous. For transmission line context, two models are used widely, JMarty and ULM. The use of them for years proved that they are robust and capable to simulate several cases. JMarty, also known as FD-line, is a model made in the modal domain. Therefore, it employs the transformation matrix. In this model, the transformation matrix is real and constant in frequency, and because of this, we have some consequences. JMarty is not recommended to, first, simulate underground cable, and second, asymmetrical transmission line configuration. But it is still recommended to simulate balanced line configurations. On the other hand, we have ULM, Universal Line Model, also known as wideband model. It is a model made in the phase domain, therefore it solves the telegraphy equations directly without needing a transformation matrix. ULM can simulate the case that JMarty can do and more. It is recommended to simulate underground cables and asymmetrical transmission line configurations. And what are the goals of this work? Firstly, the goal is to implement ULM in the Alternative Transient Program, ATP. Indeed, ULM is not new, but we can see it on paid softwares, for example. Over 20 years have passed after the creation of this model, and it is not available in ATP yet. ATP, as we know, is free for licensed users. Second goal is to validate the implemented model through comparisons with ULM with EMTP-RV. Once validated, last goal is to investigate transient on overhead transmission lines, but in this time considering a rigorous formulation of model of the soil and the per unit length parameter calculation. And how was the strategy to implement ULM in ATP? This diagram shows us how we make it. We begin with MATLAB at first stage. The user enters the transmission line data, and MATLAB code is responsible for calculating the line parameters, time delays, the characteristic admittance matrix, propagation matrix, and their fitting. In the end of this block, a text file is generated containing all information about the line, and this file acts as a link between MATLAB and ATP. In second stage, a format model reads the text file. In format model, the ULM equations were implemented in C language. The program initializes the variables necessary for calculating the transient in the first time step. And from the voltages and currents at the line terminals, the format model calculates the historical currents, feeding back the type 94 component at each time step. And finally, ATP returns the values of the terminal voltages and currents to the format model. But we have a problem in this flow. The communication between the format model and ATP has a delay of a one-time step, and if you don't consider it, the model will not work well. We solve this problem by compensating one-time step in the calculation of the historical current sources. I mentioned that here two important components in ATP that allowed us to implement ULM. First one was format model. In this element, we can program in ATP by using C or C++, giving us more flexibility. Second one, type 94. This is the component recommended to create new transmission line models because it encapsulates the Norton circuit in just one block. Two cases were considered to validate and explore the model implemented. We named the cases as Case A and Case B, and in this presentation I will show the results for Case A. The validation consisted in simulate the case in EMTP-RV and set it as a reference. We name it as ULM-RV. It uses dairy to calculate the ground return impedance. The ULM implemented in ATP is called here as ULM-ATP and it uses dairy too. And finally, we simulate the case by using JMarty in ATP. We want to see how will be the performance of this model here. And remembering that JMarty in ATP uses Carson to calculate the ground return impedance. Low and high resistivity soils were considered, in this case 100 meter and 10,000 ohm meter. Next, once the model is valid, we explore more the case. Here we simulate the same case by considering a more rigorous formulation for the per unit length parameter calculation. Case A considers two lines of 10 kilometers running in parallel. One is 230 kilovolts, three-phase line with two shield wires. And the second is a 115 kilovolts, three-phase. Both are horizontal lines. In this test case, a step voltage was applied at the sending end of the 130 kilovolts line on phase A, assuming all remaining line terminals to be grounded on terminal K and open-ended on terminal M. The voltages induced on the 115 kilovolts were studied and shown in this presentation. This graph shows the voltage calculated on phase D at terminal M. ULM-ATP is the black line. ULM-RV is the red dashed line and JMarty is represented by the blue dotted line. The simulations considered a soil resistivity of 100 ohm meter and constant soil parameters. We can observe that ULM-ATP and ULM-RV are coincident, which validates the implemented model. The Marty's curve shows some deviations when we compare with ULM, but the model performance can be considered acceptable. The observed differences are due to the fact that the eigenvectors associated with the line configuration present a variation with frequency that we cannot ignore here. We did the same previous simulation, except that now a 10,000 ohm meter soil resistivity is considered. Once again, an overlapping is observed between ULM-ATP and ULM-RV. On the other hand, Marty's model presents a small deviations due to the use of real and constant transformation matrix. As we validated the model, we can explore it more. Now we repeat the previous simulations and we are considering Nakagawa's equations to calculate the ground return impedance, Wise's equation to calculate the ground admittance, and frequency-dependent soil parameters by a Lipio-Visacro model. The models are now named ULM-ATP star and JMarty star to stress the fact that a more rigorous formulation is considered here. For comparison purposes, the same test case was simulated using ULM available in EMTP-RV. And just remembering that ULM-RV assumes constant soil parameters, doesn't consider the ground admittance and considers dairy to calculate the ground return admittance. This figure shows the case for a 100 on meter soil. It is observed that for a low resistivity soil, the results obtained with ULM-ITP are coincident with ULM-RV. This indicates that in this situation, the use of model available in EMTP-RV leads to good results in the simulation of electromagnetic transients. The result was respected here because for low resistivity soil, the influence of the ground admittance and frequency dependent soil parameters is negligible. Moreover, the voltage waveform calculated with J-Marty star is comparable to that shown in validation case. Despite the observed deviations, the model performance is once again considered acceptable. This figure illustrates the results obtained for a 10,000 on meter soil. In this case, we noticed that ULM-RV leads to overvoltages with deviations compared to the reference case ULM-ATP-. This is because ULM-RV calculates the ground return impedance and admittance using a less rigorous formulation than ULM-ATP-. Also, it assumes constant ground parameters, which is not realistic for high resistivity soils. We can observe that the voltage waveform calculated with J-Marty star is similar to the other ones at the beginning until around 0.2 milliseconds. And as time runs, it presents greater deviations. This is related to loss of accuracy associated with the use of a real and constant transformation matrix. This simplification becomes more critical in this particular case because the effect of frequency-dependent ground parameter is stronger for high resistivity soils. So, the use of ULM-ATP* is recommended in this case. Okay, here are the conclusions of this work. This work demonstrated an implementation of ULM in ATP as a foreign model coupled with type 94 component. The implemented model was shown to reproduce the results obtained with ULM available in EMTP-RV with great accuracy. This indicates that the produced ULM implementation in ATP leads to reliable results and can be used in the evaluation of the transient phenomena on overhead transmission lines with strongly asymmetric geometry. In addition, it incorporates rigorous expressions for the calculation of ground return impedance and ground admittance, as well as frequency-dependent soil parameters, which is shown to be important for the simulation of high-frequency transients on transmission lines above a poorly conducting ground. The proposed implementation is flexible and can be easily adapted to accommodate different parameters calculation strategies and different fitting techniques. Future works include the use of ULM-ATP in the simulation of transients in underground cables, compact distribution lines, and lightning-induced voltage calculations. The support files and instructions for implementing ULM in ATP are available in this link or by scanning the QR code. Thank you all for your attention in this presentation.